Hello, everyone. Maybe we can start slowly, so more people will come. So can you hear me? Okay. So there are like a few questions here. When is the due date for demo lab 1? So lab 1 is for 3 weeks, week 3, 4, and 5. So you don't need to attend for next lab next week. Maybe you can do it on like in week 5. That is right before the due date for the report. That's one. The other one is, so for lab 1, it's clear. So you don't have to attend every single session of the lab. Do it at home or whatever. If you need help, go to the TA. If you just need only like a demo, just attend the last session of each lab. And the deadline for submitting your report is February 6th. So I changed it from February 1 to February 6, which is Friday. Yes. So here I didn't see course outline for EE 8209. The course outline for ELE 88 and 8209 are the same, but the main difference is that you will not have labs, but you will do term project. And this is the announcement that I would like to say for graduate students. The group members for the term project have been formed. So I informed every single group about their members. Those who didn't receive any email from me, please email me back and start working on your term project. The last announcement is that starting next week, I will be posting some practice problems that you try at home to solve, and then I will be posting the solution. Those practice problems will be more likely same as the questions for the midterm. That will help a lot for the midterm and the final as well. So every 3-4 weeks, I will be posting one long assignment with the solution as well. But please try to solve those problems on your own and then compare your solutions with mine. Okay. Can I demo and submit my lab before my demo date? Yes, you can actually submit your lab. It's open. You can just submit it through the D2L. Will the TAs go over any? No, the TAs will not go any over tutorials questions. Is there any formula sheet? This will be decided later. Either I will bring the formula sheet or you can have your own formula sheet that is a single-sided. That should be fine. But can I do it early to my TA? Yes, you can demo your lab early to your TA. That's fine. You can even do it in the first week. If you feel comfortable about your solution, you don't need any help from the TA, you just go ahead and do it. The last day. My TA said that the last day to demo, it's not next week. It should be week 5. Next week is 4. Week 5 is the week after. Okay, so I think we are good with the questions. No more questions here. Okay, so let's start the lecture. So what did we have for last week? Last week we talked about different things. It's mainly reviewing linear algebra, which is not very important, but I would like actually you to revisit your knowledge about linear algebra, probability, and random distributions. Because when we move forward, then you will be asking, what is this notation? What is this distribution? So that's the main idea why I reviewed a linear algebra last lecture. And then we continued with optimization and machine learning basics. So if you have any question, so I have actually 2 Zooms. One is Muhammad Saif iPad, and then the other one is Muhammad Saif. Please send your chat to Muhammad Saif, not the iPad. I will not be able to reply from my iPad, but I will be replying and reading your questions from my computer. Okay, so let's start the lecture. Okay, so what did we have last week is we covered most of those things that you know, and I already posted the field notes for you just to go over it. And I will be reviewing only the important things from this lecture, which is the optimization. So we have covered much of those, but we will be reviewing what is an optimization. So you might think about an optimization like it's minimum of J omega, and we are optimizing over omega, where omega can be like one dimension or multiple dimensions. And G omega is the definition of the cost or the least square errors. And also we have another definition, which is the same. We call it like omega star. It's argument G omega. And you know what is the difference between those 2 optimization problems? If you know the answer, just write the chat. They are actually the same, but the difference is that what is the outcome of each optimization problem? So here, the outcome of this optimization problem is the value of G omega that you minimized. So for example, if you have minimum of omega and you have 5 omega minus 10 square, if you solve this one and find what is omega, which is one random, it's like one dimension, you might get it as 0. That's the possible solution, the best solution. Here, when we say minimum omega, same function, minus 10 squared, it's quadratic, convex, we will get what? What do you think we will get? We will get the value of G omega or something else. So let me see if there are like, if there is any answer here. Okay, we have few answers. We will get actually the omega that give us the minimum value, which should be 2. We will get the best omega that will minimize this function. Anyhow, this is just like a review of those like omegas and optimization problem. So now we have this kind of a function or an optimization. This is the most general one that we use. This one is also valid. So what do you mean by G omega? So in machine learning, G omega is the least square, the MES, the minimum like error square. We defined both of them in last lecture, or it can be the cost function in classification. So when we say least square, we might define it as 1 over m summation over I, where m is the number of samples or examples in your data set, and we have yi minus yi hat square. So this is quadratic. It's just the difference, the error between the true value, the observed one that you have, and the predicted one that you might get it from your regression or from your model. So how this is related to what we are doing with optimization and the gradient descent, all of those things. So now let's imagine that we have this sample of data set. Okay. And this omega I or omega I hat is a function related to ax I plus b, where b is the intercept, a is the slope. Is that right? This is how we will be defining our model in most of the lectures after the midterm. So it has a slope and it has an intercept. So usually you can optimize both of them. So omega now, it's a vector of A and B. So now we want to optimize those A and B. So how do we optimize this one? So first of all, you might wondering that, okay, I don't want to optimize both of them are the same, but for simplicity, we will say B is fixed and I want to optimize A. You know that the intercept is the one that's related to x2, for example, and here is x1. This is my representation of data. If I choose this one to be here, I choose the intercept is fixed. I don't know, it's 0.5, for example, and the slope is random. This is what I choose. Now, the machine learning model will try actually to find the difference between those points and this like fitting model. For all of them, divided by m, we will get a cost function. We will have here is A, my slope, and this is my least square, the one that I defined here. We call it cost function, or you call it MSE. So if you choose the slope is random, you might have a point is here. And this is your slope. Give it like any random value. Okay. Now, if you want to choose another slope is here, but with the same intercept like this, you might have like a very worse cost function, a value. It's not to the minimum. Now you want to build all of those because this one is square and it is convex. We will have something like this. This is my cost function now. This is representing by this. It's square, quadratic, upward, and convex. The ultimate goal of us that we are doing is we want to arrive at this point. That's actually the minimum error that we can get, which related to omega or A is here. So now, if you choose to have a different slope is like this, okay, now you are trying actually to get the best model that you will get for your data set, and you take the differences, I am sure your next point of the cost function is minimized. It's going to be here. It's going to be here. It's going to be here. Now, if you decided to go with another one, is like this, same intercept, but it's like this, you might have your cost function is going to be there. That's the minimum that you get. Means this one, based on the optimized A, the slope, minus the true value or minus the predicted value is almost zero. And you will stop. Even you started at any initial initialization here of the slope, you will get back all the way. So the main question of this is, do we actually like optimize this slope and intercept or any other thing for classification randomly or not? Or there is an optimization? So the answer of this one is big, and it is the main concept of optimization for machine learning. So last time, what we did, we said, okay, we have this one. I have this one. This is my convex function, and I want to go all the way to the minimum. The one that we learned is we divide this into uniform samples with equal step size. From here to here is equal, and so on. That's what we did. We call this is uniform sample. Make sense, guys? Okay. What uniform sampling will do is it will actually calculate or evaluate G omega at every single point, and then it will choose the minimum G omega, which is this. That's actually uniform sampling, and it has its own limitation. The other one that we studied is we have the same, but we will go with this, for example, and instead of doing like uniform sampling, we will have random. One is very close, far, close, close, far, all the way. And ending up with doing this one, evaluating G omega at every single step of this and finding the minimum. So the main limitation of this uniform and random is that it has a lot of complexity, high complexity. The complexity is going exponentially with the number of points that you are actually sampling. That's not a good solution. We don't want that, is it right? The one that we explained also, so both of them is called zero order optimization. Why we have zero order optimization? Because so far we are not caring about the gradient. We just care about the function itself, G omega. Another solution, if we have the same, it says the idea is to generate those samples such a way that it goes down. It goes down all the way down. Even if you step from here, it will go all the way down to the minimum, which is here. So the question is, how do we go down? Maybe it might go up, is that right? We don't know. You can think about that. You are standing here, you are going up, downhill, and the first thing that you will say is you will scan 360 degrees. You will see all the surroundings, and you will try to find the path that will give you down. That's actually what it says for this solution, is we will generate many random vectors. It's actually infinite number of vectors to explore, but we said it's B random vectors. And we explained this, but I'm just reviewing it. And then you will be selecting the best random vector that it gives you down, which means G of omega K should be greater than G of omega K plus 1. We're going down. This is bigger than this. This is bigger than this, and so on. If you didn't get any of those random vectors, what you will do, or the evaluation is not correct, you will actually regenerate it again, which is also not good. This is what we had last week. Let me know if you have any question about this. So we cover this one is here, and we stop at this one. Okay, so the next step is we want to find another way of first order coordinate descent. Instead of using G of omega, why we are not using the gradient? One thing about the gradient that you might learn before is that if I have a convex function like this is exactly the minimum. And if I choose any point here and any point here and take the gradient is just the rate of change at two instantaneous points. So I might have, this is my slope. This is the gradient. This is greater than 0. It's increasing. Is it right? This is also a gradient. It goes down. So if we are at the minimum, at omega 0 or omega star, then the gradient is this, which is 0. There is no slope, just straight. That's the reason why we are saying at omega 0, that give us the minimum of j omega, the gradient of g of the function is equal to 0. Means there is no slope and we are arriving at the local minimum or the global minimum if it is convex. This is actually all about the gradient. So we are not arriving at this point. So now the first order coordinate descent, it actually uses the gradient. It's not using the function itself. And then we will consider j omega and starting point. We always use like starting point to go with. So we were starting from here, but this coordinate descent is not updating your parameters at the same time, all of them at the same time, but it goes one by one. That's the reason why we call it coordinate descent. So if we have 2 dimensions, one is x, one is y, then you will say, okay, I will fix one and optimize the other. Then I will fix the other and optimize x, and so on. So what it does, it's very simple. It's actually starting from omega 0. We need to start with finding the first parameter while keeping those fixed, and then find it. Then we go to the next step. This one is already found. We need to find this and fix all of this based on the previous ones, which has values that we know. And we keep doing this one until we arrive at the minimum g of omega. That will be actually our slope and intercept or whatever classification. So here, this is the things that we need just to show exactly what this first order coordinate descent. It's going to be like taking the partial derivative with respect to this. Those are constant. Make it equal to 0. Then you find it. Is that right? If we have g of omega is omega square 1 plus omega square 2. And then your omega vector is 1, 1. This is the initialization of 0. Then what you will say, I will take the partial derivative of g of omega, j omega 1, and calculate it. Is that right? This will be 2 omega 1 plus 1 square is 1. This has to be equal to 0. Then I will say 2 omega 1 is minus 1, and then omega 1 is minus 1 over 2. Now I found what is omega 1. Then the optimization will actually go through omega 1, fixed omega 2, and go through omega 1. Here is an explanation that I gave you last time. So we're starting from this point. Since we have only 2 coordinates, x and y, we will fix the horizontal. We are not moving this. We are not moving here. What we will be moving is we will go vertical. Means optimizing over one of them is the vertical. I choose to go with the vertical. Where it will stop until it arrives the optimal solution to that coordinate, which is the partial of g with omega 2. That's equal to 0. You will find this. Now you are actually fixing the horizontal. You are not going up, but you will be actually fixing this. Horizontal is going this way. Then you fix the horizontal, then it will go vertical. It will go like this way, and it continue up to find the local minimum. It's not exactly the optimal, but you might get a good solution. This is how the coordinate descent. We are starting at an initial point, fixing the horizontal, going up, optimizing one of them, and then going there, optimizing one of them out until we arrive at a good solution that we are good. So we keep alternating between fixing omega 1 and omega 2. Exactly. We keep alternating between fixing omega 1 and omega 2 up to some iterations where we are satisfied, or whereas there is no actually like improvement. This is how we define the coordinate descent. Probably some of you will not like it. We are not using it, actually. What we use is the gradient descent. So here, the limitation of this first order coordinate descent, it actually moves in only 2 directions, either horizontal or vertical, up or down, positive or negative. But in fact, if I started with this one, so there is also a position to go here. Why I don't go here? Go here. Go here until I arrived. Why should I go up, fix, and go? This actually idea is called the gradient descent. Instead of updating my parameters one at a time, I will be updating both of them, the slope and the intercept at the same time, simultaneously, until I arrive the minimum. So here, the direction of the steepest descent is the opposite to the gradient. Let me explain this one. So you can go over this. This is like just the proof that you can read. Nothing actually here, just for your reading. And we want actually to explain the gradient descent, because this is the most important one that we will be using a lot in machine learning. So at the beginning, what we do is we start with an initialization of iteration is k equal to 0. You have an algorithm, you start with k equal to 0 and choose omega 0. Choosing omega 0 sometimes is very sensitive, because if you choose a random omega 0, it might give you a local minimum and stuck there. If you choose something else, it might go to the global minimum. It depends on how you choose omega 0. Sometimes they choose omega 0 randomly. Sometimes they choose it from an initial or optimized initialization from the resources or from the internet. So this is our starting point, okay? And then we compute the gradient. The gradient we compute it either like omega is multi-dimension or omega is one dimension. If omega is one dimension, the gradient is just the derivative. If we have multi-dimensions, this nabla, the gradient, is the partial derivative at every variable omega, omega 1, omega 2, omega 3, and so on. And now this is the most important one, is the update of the new omega k plus 1 at iteration 2, for example, relying on the previous one, omega k, minus alpha times the gradient. Well, alpha is called the step size. Alpha is the step size. And also we call it learning rate. It has actually two different names. It has to be fixed all the time. Choosing it to be very large or small, it depends on your solution. If you choose it small, then you will have to have a lot of iterations to arrive at the local minimum. If you choose it to be large, it might overshoot and jump on the local minimum solution. Anyhow, then you will increment this. So now let's see how this will work. I just did this one, this slide for your convenience. It's the same, but in a different way that the computer will understand. So here, let's say we have this, our function g omega. That 2 was power 2, right? Oh, we will come back to... I don't understand what is 2, but we will actually come back to this. So assume that we have this slide, and we have this g omega. Is that right? It's convex upward, and it has a local minimum. Any convex function, any convex optimization problem has a local minimum, which is the global minimum. Anyhow, we have this one. Now you choose to take a point here. Choose to take a point here. You choose to take a point here. It doesn't matter where you go. For example, I will go with here and find the gradient, the slope of this. And I have a function is 1 over 2x squared. 1 over 2x squared. So if I choose to go here, the gradient is increasing, then the slope is positive. Is that right? Because the function is increasing. Then we have the derivative here is greater than 0. Now when you do the update, you are actually at this point. I don't know what you call it, x1. So you will say xk plus 1, the new x is xk minus alpha minus something, minus alpha times something. The whole thing is positive. The whole thing is positive because it's increasing. I'm saying it's here greater than 0. It's increasing. When you say x of k minus alpha times a positive, it means that we are going here. x1 is 10 minus 2, I will get 8. 8, then I will get 6, and so on. I will go here, then I will go here, I will go here, I will arrive at this point and stop. That's actually what the gradient means. It actually means what is the best path going downhill opposite to the gradient. If the gradient is greater than 0 going up, I will be going down. If you choose to go here, if you choose to decide your starting point is this side, you might say the gradient here is less than 0 because it's decreasing. Is that right? Then I will say minus and minus is positive. Now I will have to go here. This is my x1, which is, for example, minus 5. And this is 0. Then I will increase it because minus times minus is increasing here. Then I will go here. So I will go here. So the main point of the gradient is that we are going opposite to the gradient to the steepest descent up to this point, and we stop. This is all about the gradient descent that you will be dealing with in this course. And this is the main step. Here, this one is just normalization. We don't need it. When you do your coding, you don't need it, but this is just to make sure this omega or the Euclidean distance of this, it doesn't affect our solution. Okay, guys, so here is the solution. Some of the examples that I found, I will give you the code for this. So you're starting from here. So now I am not going into one direction, the coordinate descent, either up or down. I'm going actually in the direction that will give me the gradient descent up to this point. You go with this, you go also with this. Okay, guys, I will pause for a few seconds if you have any question about the gradient descent, because it's actually the main point in lecture 2. The others are just like reviewing of linear algebra. So that 2 was power 2, right? Where is the 2? Maybe if you are more specific, in which slide? Yes, so the gradient descent moves in 2 directions at once. Yeah, that's actually a good point. Can you summarize the main points we need to know for this concept? Okay, that's okay. So the summarization of this one is you actually want to update omega. This is the best summarization that I can conclude with. You want actually to optimize or find the best omega that give you down to the minimum value that you will have almost error in your regression or your classification. And this is like G at omega star. It's almost 0. If assume it's close to 0. So how we update this one, we use the gradient. So we go with opposite to the gradient descent. Yes, exactly. So now this is applicable, this one, or this one, applicable if it is 1 dimension or 2 dimensions. So if it is 2 dimensions, what do you think, how it works? 1 dimension is just like you update. For 2 dimensions, you will be updating both of them simultaneously. So for example, let me see if I can write something here. Okay, this one for the slope and then for the intercept. I will go with omega. It's like a scalar, omega k plus 1. We'll say it's 1 equal omega 1 of k minus alpha. Then we have the partial of g, omega 1, omega 2, and of g omega 1. And this is known, and you need to find this one. Okay, so now you find this one. Then you will go for the other one, omega 2 k plus 1 is equal omega 2k minus alpha, the partial derivative, omega 2. Before, when we had the coordinate descent, we were optimizing this one and stop at this. We fix it. Now we are doing this one simultaneously. And then you combine this and this, you will call it, this is a vector, is a vector omega, which is here. I hope this is clear. We normalize the gradient vector by dividing the norm is just to make it a unit length, just to make it a unit length. Because that normalization, it goes by unit length, but who will actually determine the step, the jump that you will making is the step size. Who will actually determine the jump from here to here is alpha. In the denominator, L2 norm. Yes, that's the L2 norm, the Euclidean norm, correct. Okay, guys, this is all about the gradient descent step size. If it is like small, if it is large, this is something that you don't need to worry about. This is just for your coding and project or for your labs. And also there are 2 ways to choose the step size. Either you have it fixed during all the iterations, or you just need to have 1 over k. And we also, I also taught this one. Alpha is 1 over k. What does it mean? Alpha is 1 over k is I will actually design my step size in the way that it decreases when I increase the number of iterations. So when k equal to 1, then 1 over 1 is 1. That's my step size. It's a little bit big. Why it's big? Because I'm still far away from the minimum error. I'm still far away. I'm still here. and the error is here. I want to jump. If I just jump slowly, I need a lot of iterations. But I want at the beginning to have like a big jump. Then when I move forward with increasing the number of iterations, then k is increasing, then alpha maybe 1 over 10.1. So now instead of jumping by 1, I will be jumping by 0.1. If I'm here, then I will be jumping a little bit slow to not overshoot or to not jump to here. Okay, guys, this is just a simple way that to memorize. So there are like some criterions that we need to stop. One of them is if the gradient is 0, and we know that if the gradient is 0 means we are actually having a slope of 0, or there is no any update between omega k and omega k minus 1. Like the one that you will get for the next step is same as what you got now. There is no update, where 1 over n is the number of samples. And here the function values don't actually different. So for example, here, this is the one that you got. The next one is very tied to it. So there is no improvement anymore. Instead of keeping doing this and waiting for your code, just stop and do something else. Or you can set the maximum number of iterations at the beginning and then you stop. For example, you put it like 50. Most of those like figures I did when it is like 50 iterations. So here is like a very simple code that I will be posted for you when you do the gradient descent. So here, you just go over it. What I have here, this is my function, omega squared. That's the reason why I have this shape. It's like, it's same as x squared. Okay, and this is my gradient, 2 omega. That's my derivative. It's only one dimension. And here what I define, it's just the history for weight, omega, and the history for the cost. This is the cost. This is the weight. I choose from here. I starting with this point. I don't know what is this point between 2 and 4. Then I update it. Go here, all the way down, up to this point. And this is the code. Okay, guys. So let me see what's going on here. Please do this one. I will post the solution for this. Express the gradient of the function, evaluate the gradient at this point, and then do the gradient descent for this omega. I will also post like one big problem about finding the gradient descent for 3 to 4 iterations, a little bit complex problem. And this one is you have the solution. Is just a proof for your reading. It's not required. Is that we are indeed moving into the opposite of the gradient descent. Opposite to the gradient descent. This is opposite of g of omega. And this one is mainly for graduate students. If you have time, you do this one. It's something for finding the Hessian of the function and also proving that the function is convex or non-convex. So usually what we have, when we have first order and then we have gradient descent, there is also one more very efficient algorithm that it actually jumps to the minimum with a small number of iterations. It's called Newton. That actually relying on the second derivative, it's the Hessian. Before I move to the next lecture, please let me know if you have any question, because the next lecture is completely a different topic and we want to set our mind into that topic as well. So I will give you like a few seconds. If you have any question, just let me know. This is the remaining of last lecture that we couldn't finish. What is the difference between the gradient and the gradient descent? The gradient is just the partial derivative of function. The gradient descent is the algorithm itself, where it goes to the steepest descent or the ascent. So it's actually just the wording different. So the gradient is usually used for in math when we say, okay, if you have one dimension, it's the derivative. When we have multiple dimensions, it's called the gradient, which I represented by nabla. Gradient descent is a more term that for machine learning, which is the algorithm that we update omega. It's going through the steepest descent to the best that we can go for minimizing the error. Okay, that's true. So the gradient is just a general term. We use it to take the derivative of a signal per one variable, but the gradient descent or ascent is just the direction is going up or down. Usually we go up. So the question is, if we have a signal or a function, it's not upwards, it's like this. It's like this. So what you should do with this? Usually what we do in most of the lectures that professors are teaching is we do this one because this is an easier one to explain. It's convex, it has local minimum. This also upward, but it might be has a different explanation. It should be the same. So in this case, what should we do with this? Let me see some answers before we move to the next lecture. So here, is it minimization or maximization? It's max, correct? It's maximization. So now if you go with this, if you choose a point here, so now most likely your algorithm will not go point. And so the gradient is ascent. Exactly. So here, when we say it's convex, upward is gradient is descent. It's like going down. But for this one, you choose an initialization is here, your starting point is here, and then most likely you will not go down, is that right? Unless you don't want your algorithm to be efficient. So what you will do, you will go with the gradient ascent. It's going up, up, up to here, which is the maximization. The way around that you might think of, if you multiply this one by minus, then you will be minimizing. What I will do, I will actually multiply this one by minus and put it like this way and follow my regular algorithm. That's the reason why we say maximization is same as minimization, the negative of the function g omega. And we had that one before in last lecture. Okay, so let's continue with lecture 3. So I don't see any questions. So now we learn a little bit about optimization. We learn about gradient descent. We reviewed some linear algebra things. Now we want to go to something is called the Bayesian decision theorem. It's like a theory to decide which class we will use or which class we will decide. This is mainly as a classifier. You will see a lot of classifiers. This is one of them. So who knows about this BDT? Do you have any knowledge about this classifier? Is it a machine learning? Is it a model that we learn? It relies on what? It's a little from lab 1. That's true. This actually is the topic of lab 1. So most likely, if you did this, if you already did the lab, then you have good knowledge about this BDT. But if you didn't do the lab yet, we will actually explain it today. So it is a probabilistic model. It's statistical. It is probabilistic. I know Bayes probability. Yes, exactly. That's actually the Bayes classifier from probability course. This is called Bayes classifier. It's called Bayes rule or Bayes classifier. Okay, so let's start. So the BDT in a nutshell, it's actually used training set of samples of the data to derive some basic probabilities. So those who answered said it's probability. Yes, it's a probability model between our data sets. So we use these probabilities to make a decision. So our decision is not based on gradient descent or any machine learning. It's based on some probabilities. And then we will use them to categorize our unseen data samples. So you will actually do the probability of the model. And then if there is any unseen or next data sample, then you will use that model to actually guess what is the class of the unseen model, of the unseen like data samples. So now let's go with the classification example here. Assume that we have a set of fishes and we want to classify those set of fishes into different classifiers. So usually we go with C classes. Most of the time we will be using C as number of classes. But at the beginning, we will be starting with 2. When we have 2 classes, we usually call this one is binary classification. It's binary classification. It's plus, minus, it's +1, -1, or omega 1, omega 2, or yes, no, spam or not spam. Those called like binary classifications. So now the simple approach that you might see is how to classify the sample of data sets into omega 1 and omega 2. So we have, this is the sample space of my classification, and I divide it into 2 classes. This is omega 1, and that's omega 2. So now the question that we will try to answer is, given a sample X, please make a decision X either belong to omega 1 or X belong to omega 2. So in this case, if you don't have any model, if you don't have any machine learning, what do you think? What do you think he will do? And also it is noted to actually mention that sometimes I use category, it's class, sometimes I use class, sometimes we use state of nature. Those are the same name for class. It's like different names. This is actually related to your reference that I followed, but most of the time the correct one is class. So the question, okay, so I have a few answers here for my previous question. Will it be in both classes? Okay. What is the symbol between X belongs to omega 1? This means actually X, this is like this, in X in omega 1 and X in omega 2. And this is OR, either in omega 1 or in omega 2. Because when we classify one, we don't say it's for both, either in 1 or in 2. So the first thing that we will actually be doing is we will say omega 1 is my type of fish is salmon. And then omega 2, I will have it like sea bass. So now, if I have any unseen sample of those fishes, we want to classify is either it's salmon or sea bass. So the basic way of deciding which category on unseen fish belongs to, you will use something called prior knowledge. What do I mean by prior knowledge? So you will say if B of omega 1 is greater than P of omega 2, the prior knowledge of my class, we will decide omega 1. And I will explain what is B omega 1, B omega 2. Otherwise, I will say decide omega 2. Okay, so I am your professor for this course, and I know that there are a lot of good students. Is that right? This means I have prior knowledge, prior probability about you guys will pass the course, or you will get A+, A, B+, and so on. I have prior knowledge. Is that right? I will say 70% of my students will get high grade, 30% will get low, and some of them will fail. This is just prior knowledge. Is that right? It doesn't reflect to your performance, but it's just like a prior and random knowledge that I have about you guys. This is what we call prior knowledge. So let's say we have this example. And also we would like to mention that it's the probability of omega 1 plus the probability of omega 2 is equal to 1. That's actually the total probability of being in 1 or being in 2. It has to be 1. So if we have 2 classes and you don't care about the priority of being 1 or 2, you will say 0.5 plus 0.5. But we don't want to do that from now. So this is called the prior probability of a fish being salmon. And this one is the prior probability of a fish being sea bass. Let's take an example to explain this. Okay, so the example is saying that we have sample of categories we have like 10 samples. Those are examples from my dataset. And we have two categories, either Salomon or CBAS. This is called dataset. Well, you might have, when you do your own machine learning, you will have a lot of datasets, thousands and millions. Is that right? But for this one, we want to see, we have those 10 samples, and we want to explain what is this simple approach. So now we can classify this one as Salomon is omega-1, Salomon is omega-1, CBAS is omega-2, Salomon is omega-1. So we want to count how many of them are Salomons. And then we will calculate the priority. So how many of them are Salomons? 7. 1, 2, 3, 4, 5, 6. Is that right? So we'll say the probability, the prior probability of omega-1, this is Salomon, is equal 6 divided by the total number of samples by 10. Is that right? That's the prior. I know how many of them. I will divide by the total number of samples, and I will find the probability. This makes sense. Is that right? Which is 0.6. So now B of omega-2 is the number of them for my initialized data set. This is not for testing. This is for training, which I know I have an access to it. Is that right? B omega-2 is equal, which is for how many of them? 1, 2, 3, 4. The remaining. Is that right? 4 divided by 10, which is 0.4. So now the total of this has to be 1 because we have only 2 classes. There is no way for another class unless we will define next another class. So based on this previous slide, we would actually choose omega-1 if B omega-1 is greater than B omega-2. I know the total number of Salomons is greater than the total number of CBAS, so I will guess most likely the next one that I will predict is Salomon because of the huge number that I have for the dataset. And actually it depends on the time of the year. Sometimes you might have more Salomons than CBAS. Is that right? There are many factors, but let's keep it simple step by step. So omega-1, if B omega-1 is greater than B omega-2, and we will decide omega-2 if the prior probability is, sometimes we actually do this. It's called B omega-1 is greater, less B omega-2. If you go this direction is omega-1. If you go this direction is omega-2. This is just a different way of defining this one. So in this example, if I have a new sample that I ask you, what should you guess? What you will guess? We will stop here, guys. We will continue at 7:10 by learning this example as well. But if you have any question, just let me know from now. I will be online, so just replying to your questions. So one of them said omega-1. That's correct because the prior of omega-1 is greater than the prior of omega-2. We have more Salomons than CBASs. Okay, so what the project is after what else are we expected to do? After finding and reviewing research papers and samples. Okay, for this question about the term project. So first of all, you need to find a research paper, and then I believe that you did. And then you also find the data sets, which is good. So now start actually writing your proposal. In the proposal, what you will do, please choose a title, summarize your proposal. So say, okay, I will do this, 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 this. And then I will expect 1 page or 2 pages of literature review. It's basically from the research paper that you have or you decided to go with. And then you will have some references. The last section, just like section or subsection, it should be your methodology of what you are going to do next, which is the main report and the presentation that you will give me at the end of the semester. Okay, I would actually say, okay, if you are regenerating the results from this research paper, that would be good. If you have an extra novelty, uh, if you have extra novelty, then that will be also perfect. But for my grading, I will not actually grade the term project based on the novelty, but I will grade it based on your understanding, the way that you presented your term project, and also based on the report. So we don't have. No, you don't need to write the code for the methodology. Just explain what is your methodology in English words. For our team, cost-sensitive decision making. Okay. Okay. So I think you are asking about the title, is that right? So you are asking about which title you are choosing, cost-sensitive or simulation of cost-sensitive. If you are asking about which title you will go with, it's fine. No, I mean, is this topic? Yes, you need to do simulation. So how you will actually present your term project if you don't have results or simulations? What journals do you recommend for reading? It's actually a term project. If you are going with the IEEE transactions, it might be difficult for you to generate or regenerate most of their figures. Sometimes it's very difficult to do in a short time. But if you find that something is you're really interested in and you know that topic, it might be easier for you to regenerate. And it's also good if you find a limitation of one of those journals and you say, okay, I will propose this. Then we will be like proceeding with the publication. But if you have a good conference that has like a good contribution, you don't have to go with the journal. Conference would be sufficient. No, you don't need to demonstrate novelty. Regenerating like a research paper is enough for me. But again, if you have novelty, that's an advantage. How do you recommend we start lab? Okay, for the lab. Okay, for the lab, you have a TA, is that right? So you need actually to attend your lab session, sit with the TA. They have my solution and the code. They will actually help you out. Probably for this BDT, you might get some knowledge, some information from my lecture, and then you will be applying that one for your lab. But anyhow, if you don't know how to approach for the lab, actually ask your TA for that. And the thing that this time we're actually using Python. Most of those labs have been done in MATLAB, but this time we are actually using Python, which is really good for machine learning. And also it's easier to do machine learning with Python. There are a lot of resources you can do from internet. Yeah, if you send me an email with your group members, so I don't have to reply you back. I just send emails to those who don't have any group members. I assign them randomly, but if you already have your group members, you send email to me, then I will not reply to you. I will just make a note in my site that you have formed and will be expecting your proposal by February 28th. So again, what is expected? Okay, the proposal is you need to have like a final title, summary, literature review with some references, and methodology for your term project. That will be the final. Yes, the final delivery for the project is your report, your code, and presentation. Presentation will be like around 15 minutes for all of you guys in the same group, and that will be the final one. But the proposal is just like 5% of your term project grade. So you have 30%, 5% is for the proposal, and the 25 is your for presentation and the report. No, we will have actually our own like presentations, just me and the group members. Even the other group members will not actually be attending the presentation of different groups. And this actually presentations will be outside our lectures because we have around 14 groups. That will take a lot of time. So we will be like outside our lecture time. Do we need to simulate the literature? No, you don't need to simulate the literature review projects. Choose a paper and simulate it. Try to regenerate their results. Choose your topic and design a new algorithm and do simulations. That's also good. If you are good at machine learning and you have a topic in your mind, it's not related to your PhD or master's, why not? But in general, the easiest way is just to pick a research paper conference, simulate it based on their settings, and present. It's easy. Okay, so we still have 1 more minute, or we can wait a few more. Yes, if you select a novel approach, yes, then you need actually to compare the results that you got with the related works. That's true. Because if you have your own novel approach, how do we know that your approach is better than others? You need to compare. Machine learning or deep learning model, it's fine. Machine learning model will be fine. Deep learning model will also be good. Okay, guys, let's start. Let's start from here. Okay, this one, let me just erase it. So now we have actually omega 1 or omega 2, and we have B omega 1 is greater than the probability of class 2, the prior probability. Sometimes we write it like this, B omega 1. Some of the students ask about it. So we have is greater B omega 2. In that case, we will select omega 1. If it is less, we don't have to write it again. We will say this is omega 2. Okay, just a different way of notations. Yeah, it's greater and smaller. The proposal due date is February 28. Okay, so in this example, what do you think we would choose most of the time? All of the time. What we will choose? Definitely we will be choosing omega 1 because it's fixed and B omega 1 is always greater than B omega 2 unless you change the data sets and change those probabilities. Probably you might have an extended data sets with more sea basses than Salmons, then you will say B omega 2 is greater than B omega 1. But for this fixed and training data set, we choose omega 1 all the time. Therefore, B omega 1 is equal 0.6, which is greater than B omega 2 of 0.4. So A few like notifications here is the decision is independent of observations. Yeah, but it is not always Solomon. Yes, that's true actually. It is not always Solomon that we will get, but our actually algorithm is not that good, is it right? It will give us like an error all the time if it was CBAS. That's actually, this is not an optimization, this is just a simple approach. So even if your fish, the next fish is CBAS, then the algorithm will always select Solomon. That's actually the limitation of it. So then we'll say, however, this decision is independent of observation. First of all, this decision is independent of my observation. Even if you observe that it's CBAS or you observe that CBAS, then the algorithm will give you all the time Solomon. So here, the decision, this is other notice that is always omega 1. So what is the error now? So 60% of my decisions will be omega 1, which is correct if I choose to go with Solomon, and then 40% is incorrect. That's actually for CBAS. If your new data set or if your new sample is CBAS, and then you actually categorize it or you classify it as Solomon, then you have an error of 40%. 40% of your selections is in error, and 60% is accurate. So is it clear with this? It's a very simple algorithm that does not rely on machine learning. There is no model here. There is no machine learning model here. There is nothing. It's just like relying on the prior knowledge of your data set. So now if you have, for example, like if you have another class of a different type of fish, but most of the data set, the training is for that class, then we will be choosing that class and ignoring Solomon and CBAS. This is also another point if we have multiple classes. Okay, I don't want to go over this slide. So how do we optimize this? How do we avoid this? Your decision is always omega 1 and is like incorrect with 40%. So how do we optimize this? How do we improve this simple approach? Okay, the next step that machine learning, yes, this is one thing. We will use machine learning, get more priors, posteriors from the features. This is actually correct. We will actually go to the posterior of the classes from the features. Okay, we will go to that point, get more priors. I don't understand what does it mean, get more priors? Means increasing the priors of CBAS. Okay, let's go step by step. So we will call this one is an observations and decisions. So for example, you actually come to my office and you ask me difficult questions, hopefully not. And then I will have actually some observations that you are a good student. You know actually the topic and you ask a very good questions. This is an observation about you. Is that right? Now I have some knowledge about you. So now if you think about Solomon or CBAS, they are not equal in length. Is that right? They are not actually equal in length or in lightness. They might be some differences. Definitely they are not identical. You might have some differences. Those differences, we call them features. We will actually use those features to actually like propose a model called posterior. We can relate features to classes. Exactly. So what features are more likely related to classes? That's actually a good point. So now what we'll be doing here, we condition our decision with a additional measurable information. We will actually add more information to our model to have an accurate decision. Instead of having it fixed all the time, omega 1, omega 1, omega 1, we will actually test the new sample. What feature does it have? Does it have like good length, large length, short, tall? It has good lightness. Then based on that, we will see if it has Solomon feature or it is CBAS feature. From the training set, we can investigate how a feature differs for each class. So for example, if you give like machine learning set of classes, a lot of CBAS, a lot of Salamons. Machine learning model will actually learn those features. So it will say those CBAS that I have label of, they do have a length of less than 10. And then this one is greater than 10, it's most likely CBAS. Also, you have the lightness here as another feature, and that's actually what we will be using to actually develop the posterior. So now, instead of having a fixed probability, prior probability, we will have something for feature. So let's go with this one. So we have BDT, where we have omega 1 as a class. This is the sample set. Are you like saying posteriors? Yes, we are saying posteriors. So we have the sample space of omega 1. And this is my feature. Part of my feature belongs to omega 1. For example, if it is greater than 10 or it is less than 10. Part of the feature, if it is more than a value, it might be for omega 2. Let's actually see what is this intersection. This intersection area is a samples that belong to omega 1 and have an observation X. So now, if my own observation is length, which is 10, then I will say, most likely this is Salomon. It has an observation of X equal to 10. Now, I have new information about my decision. So I'm not actually caring about the percentage of the priors too much, but there is also another factor to change my decision. So now we will use those observations to condition our decisions rather than relying on fixed thresholds of B omega 1 or B omega 2. Okay, so let's go to the conditional probability. We learned that from the linear algebra. So this intersection, we will explain it again. This intersection actually means that what is the probability that samples belong to omega 1 given that it has a feature X? This is the intersection. Sorry, this is the intersection. It says samples that belong to omega 1 and have observation of X. Can be 10, 6. If the X is 15, then you will say that's actually CBAS. So the question is that I will be arriving on later, how do we model this? That's the main problem. That's the main question actually we might ask ourselves. How do I get this? If I got this, then it will be easier for me to find the posterior and actually calculate. But we will go to that point. So now, building from the beginning, from scratch, we have conditional probability. The conditional probability is that the probability of X given omega 1, the probability of a sample has feature X, it's given in class omega 1, it's the joint probability divided by the prior. We know that, is it right? And the same thing, the probability of omega 1 given X is the joint probability. It's same either that way or this way divided by Bx. So now from those two probabilities, this one and this one, we have a common factor, which is the joint. I will say from those, B omega 1 joint with X is equal B omega 1 joint of X from the second equation, which is Bx omega 1, B omega 1 equal B omega 1 X times Bx. What I'm looking for is the posterior. This is the posterior actually. This is the posterior. So we'll say B of omega 1 given X, what is the probability that sample has a feature X, it's in omega 1, that's called the posterior, is equal B of X omega 1, the prior, divided by B of X. And we will be defining most of those terms. Okay. So now what each of those terms mean, that's actually called, we will explain those everything in details. This is called the Pius rule. The Pius rule or the Pius formula. So it has three terms. The first term is B omega 1, which is the prior. We know it from our training data set that Salomons are more than CBAS. It's 0.6 and that one is 0.4. And we don't want to decide based on that. What we'll be deciding is that we have a likelihood. This called is the likelihood that we will be actually modeling. It's coming from here. This is called the likelihood model. What is the likelihood model? That X given omega, is that right? And here is the posterior. That's what we are actually calculating. We will define this one later. So now let's say we have a lot of classes, not only 2 classes. If we have a lot of classes from omega 1, omega 2, omega C classes, and we have X is the intersection between all of them. So the first thing of those things is, if we can generalize this from omega 1, omega 2, omega C, we know that they are not intersected with anyone. Is that right? This is alone, this is alone, but the only mutual between them is X. So probably omega 1 mutual exclusive of omega 2 is phi. They don't intersect. And the union of them is omega. It's the sample of all classes. So now if you give me any X, any value of X, definitely I will choose one of them. That's actually the sample space. And what is this probability, Bx? You can see that Bx is independent of being omega 1 or being omega 2. It's just a scalar. It's scalar, which is the evidence of the feature X that is belong to omega 1 and belong to omega 2, which is defined by the joint of X being in omega 3, being in omega 2, being omega 1, being in omega C, being in omega 4. It's just a constant. We need it just for convenience, but in general, we don't need it. Even you choose omega 1 or you choose omega 2, we don't need it. So now if you simplify this one, we have Bx of omega 1 likelihood. This is the prior, and this is the scalar that we don't need because it's actually same for every single class. So now let's define each of those terms. That's actually what you need to memorize for the midterm or for the final. So now we have this term. This is called posterior. It's actually what is the probability of a sample from class omega I after we observe that the sample has a feature X. So you give me like a sample, a new sample. I know that this sample has a feature X, 10 length or 6 lightness. I want to decide, is it belong to omega I, omega 1, or belong to omega 2? So to calculate this, what do I need? I will have to know the likelihood. How likelihood this X being in omega 1, how likelihood this X being in omega 2? That will be given, and we will model this. The prior probability is also given based on the training set, which is 0.6 or 0.4, based on which class. So this one will be given. This one we will need to model it using probability model, normal distribution, and we don't need this one. So this is called the Pius formula. The prior probability and prior knowledge are the same. Yes, prior probability and prior knowledge are same. And this is the scaling factor. So now let's go forward with this BDT. So the question is how we model this likelihood. In general, that will be given to us. If you don't know it, then we'll ask machine learning model to give us like a model. Usually, if you have a data set, and these data sets, you want to generalize them, how we will generalize them? If they are not actually real measurements, probably you will say, I will model my data set using normal distribution. Then that will be the likelihood that we will get. You will get a normal distribution like this, and you will get another normal distribution like this. And this is your likelihood. This is actually what we do when we have like data sets in machine learning. When you do this one, for example, if you have a set of classes, this is class, this is another class, here is the point, is that right? If you want to model this one as a normal distribution, you will say, I have to know the mean and the variance. This is the mean, and this is the mean, and the weight of this one is called the standard deviation or the variance. So in general, we'll go step by step, but later on, we will actually model those likelihoods as a normal distribution. But let's go with this one. So assume that you are given those likelihoods based on your measurements, which here is given by histogram. This histogram means that I have a lightness as my feature. if my lightness is 4, then how many counts I have Solomon and how many counts I have CBAS? Is that right? And this decision is just the decision between being Solomon or CBAS. We will not jump to the decision, how do we design it, but we will just calculate those things. So again, how we will get this model, it will be given to us, or we will be model it using normal distribution or any other distribution. But in this course, we will be focusing on a normal distribution. Now, if you choose Bx equal to 9 of omega 2, this is 8, this is probably 9. This actually means that we look at class omega 2, and what is the probability of that sample being in class 2 that has x of 9? So you will say, if this is 9, I will have it is here, probably. If it is here, I will have it is there. This is my likelihood. Is that right? And for the other class, Solomon, I have 0. Then I will say B of x equal to 9, given omega 1 is equal to 0. B of x equal to 9, given omega 2, I don't know how much, it's 8. Then I most likely will say, based on my observation, with a lightness of 9, the likelihood for this one will decide for CBAS. So now, instead of relying on prior, we will have to rely on 2 components. We will have to rely on 2 components, the prior and the likelihood that is given to us as an extra information to decide. Okay, we will move forward unless you have question about this. Okay, so now, how do we decide about omega 1? So we will decide omega 1 if the posterior omega 1 of x is greater than the posterior of omega 2 of x. Then we will decide omega 2 the way around. It's if it is the posterior of my is greater than. This is actually in just 2 classes. But if you have multiple classes, you will have to actually compare each class with all the others, and then you will choose the major vote. That's a different story. Let's go one by one for only 2 classes. So this is one way to define, or you will have to define it as that rules. You will say this one is B of x given omega 1 likelihood, B omega 1 divided by B of x, the scalar that I don't need it. It's just to complete my variable. It's greater than bx omega 2, b omega 2 divided by bx. This is just a representation of this, and the other one is a representation of this. So we have those cancelled. Then our decision based on bx omega 1, b omega 1 greater than bx omega 2, b omega 2. So before, we were actually relying on this in the symbol method that you guys said it's not efficient. But now we do have some information, the likelihood that we need to use to combine both of them and compare. Okay, so this is actually the decision rules for bx omega 1, bx omega 2, and we will continue with this example. But before I go to this example, do you have any question? So is the prior, so there is no questions here. There is a question here. Yes, we can actually calculate bx. So if we go back to here, so what does it mean bx? Bx actually means that the joint probability of x being in omega 2 plus the joint probability of x being in omega 3, in omega 4, in omega c, which is here. The joint probability of being in C, which is I equal to 1, plus I equal to 2, plus I equal to 3, and so on. This is how you calculate Bx. But sometimes we don't need it unless we want to see that the summation of the posteriors are equal to 1. That's true. In sections where the data sets overlap, we will actually go to that point. That point is really important because the intersection where those normal distributions or the histograms overlap, that will create a noise for us. Would we just have the calculation that you just did and then see which give a higher probability? Yes, we will actually be based on that. Any other questions? If no, we will have to solve this. Okay, let's go with an example with a single feature. For example, you would say it's length for fish, lightness for fish. Here I'm considering as a weather condition as my feature, and the classes is either to play or not to play based on your observation about the weather. So we have here, let me write with a different color here. So we have this one is my feature, and this is my classes, play or not, yes or no. Those called the labels or classes. So the question is saying that, and I will actually post some problems about those, like single features problems. So the question saying that using Bayes rule that we used or that we learned from the posteriors, classify or predict whether to play or not to play based on the weather condition. So I'm giving you here a set of data set here. This is actually the first column is for the features, is raining, sunning, overcast, and so on. So we do have 3 features. This is one, this is sunny, and this is overcast. So we have only one feature, but this feature has different values. You can think about them as, if this is X, my feature weather, this is sunny, rainy, and overcast. Usually we say this one as numbers. Do you remember when we say X equal to 9, means that one instant of that feature. This is 9, this is 8, this is 7. Here we don't have those numbers. We have type of that feature is raining or sunning or overcast. I hope this is clear, how to define the features in this. So with this example here, we cannot actually solve it as is because we want to transfer this dataset model or this table to another table that it's understandable as probabilities. What we will do, we will transfer this actually table into another frequency table. It's called frequency table with numbers, not with words. Is that right? So now we want you guys to go over this one. So when we have overcast, this is like one instance of the feature, second, and sunny. So when we have overcast, how many of overcast are no based on the classes? We have 0. Is that right? It's 0. So how many of them is yes? So we'll have 4. You just need to count them from this dataset table. Okay, so now for rainy, what we will have 3, 2, and we will have 2, 3. Is that right? That's actually is the numbers that we got from the dataset. So now here you have a total for no, for saying no is 5. For saying yes is 9. And we have for overcast, either no or yes, we have 4. Either no or yes for rainy, we have 5. And we have 5. The total number of samples is 14. So we have 1, 2, all the way to 14. So we have 14 samples. This is actually how we transfer this. You don't need to worry about that. You might get this one as is. It's ready. So now the question is, we want to estimate the posterior of class yes, and the feature is rainy. And also we want to find the probability or the posterior when the class is no, but the feature has a unique raining. Yes, and rainy or no raining. So what do you think? What we will do is we will be using those like Bayes rule, the posteriors. So the posterior is defined as we explained, is going to be like this one. Omega I given x is the likelihood times the prior divided by a scalar b of x. Let's define those parameters. So omega 1 will be defined as yes. Omega 2 will be defined as no. Omega 1 class, omega 2 is another class, and x is raining. We just want to transfer everything from English words to numbers and notations, because this is X. This will be X, okay? So now, what is the probability of raining? Probability of, what do you think, guys? What the probability is of this? B of X, where X is rainy. So 5 divided by 14. Exactly. The probability of raining is 5. It's from here. I'm not saying yes or no. I'm just saying the probability of rain. Is it right? It's 5 divided by 14. 5. The number of rainy that actually appears in two classes, yes or no, divided by the number of samples. And then we will have the probability of yes. I think that's also easy. Waiting for answers, or just we go ahead? So it's 9 over 14. The probability of no is 5 divided by 14. Clearly, this one is prior. This one is prior. This one is a scalar. We know it. It's rainy for either omega 1 or omega 2. Okay, guys? That's a good one. So now, definitely, the prior is given to us from this data set. This is like, I'm saying it is scalar because it's usually not needed. This is what I'm saying. When I'm saying scalar, means it's not needed because it's independent, either omega 1 or omega 2. It's raining for everyone. Yes, I will be posting this solution. The whole solution will be posted. Okay, just like follow me and understand. So now, what is the probability? Because we need to define this. This is the most important one. To define this, we need to have the joint probability and the prior probability. Prior probability is there. We have it. So now, what is the probability of raining and yes? What is the probability of raining and no? Can anyone help? So here, when I say this one is called what? Joint probability. So we will have this one as, okay. Let me see the answers. 2 divided by 5, 3 divided by 5. Why is that? It's not condition. It's not a condition. Exactly. The one who said 5 divided by 14 and 9 divided by 9. 9 and 5? No. 5 divided by 14, 9 divided by, no. Think about it. Rainy and yes. How many of them? Is 2. Is that right? Divided by the total number of samples. This is not a condition. Yes, exactly. Now there are a lot of good answers. So here, rainy, here, this is rainy and yes, 2 is the intersection of rainy and yes, 2 divided by the total number of samples. See, I am not dividing by 9 or 5 because this is not a condition. I'm just saying yes and rainy over all the samples. So what we will have, I will have 2 divided by 14 and 3 divided by 14. That's actually what that does mean, rainy and yes or rainy and no. Okay, so now we learn, let me write with different color here. We learn that the probability of raining and yes is equal the probability of rainy condition yes, probability of yes, prior. This is actually like a formal definition in probability. This one is given, we know it. It's 2 divided by 14. This one is the prior, it's here, 9 divided by 14. We just need to calculate the probability of rainy and yes is equal the joint divided by probability of yes. This is called the likelihood. That's what we are looking for. This is the feature X given yes, and we will do the same. Is this an exam style? Yeah, maybe. That's an easy one. Okay, so now what is the probability of rainy and yes? It's 2 divided by 14. And what is the probability of yes? it's 9 divided by 14. Those will be cancelled, and we will have 2 divided by 9. Actually, think about it again. It comes actually 2 divided by 9. We don't need to go over all those processes. Go to the table and see here. It's raining and yes. Is that right? Raining and yes. It's 2 divided by 9. It's a condition. Rainy, the number of rainy for yes is 2 divided by the number of we are saying yes. It's 2 divided by 9. You don't have to go over those things that I explained, but that's what actually like a simple development of finding the likelihood. But since it's a condition, I will not be dividing by 14. I will be dividing only by those who are yes. Okay, guys, that's 2 divided by 9, the first one that we did. And similarly, I will not explain that again. The probability of rainy condition no is equal rainy. Okay, I don't want to explain this one again, the joint and so on, but I will have to go with the numbers. 3 divided by 14 and 5 divided by 14. 14 will be cancelled, and we'll have 3 divided by 5. So now, from here, you got the likelihood of 2 divided by 5. You got another likelihood for saying no is 3 divided by 5. What do you think about the decision? What do you think about the decision? Which one we would choose, class yes or class no? Based on the likelihood only, not the prior. I'm not arriving at the prior yet, or the posterior yet. 2 divided by 9, 3 divided by 5. Exactly, we will actually decide 3 divided by 5 because it's greater than 2 divided by 9. But that's not a guarantee, because the posterior, we will actually like, it relies on 2 things. The likelihood, this one, and the prior of this class. It also relies on this one and the prior of that class. So most likely we will say no for now, but let's see. So now we have everything is here. We will calculate it the posterior now. It's yes. Posterior is always starting with a class. Likelihood is always starting with a feature. It's the way around. So it's the probability of rainy and yes, probability of yes divided by the B rainy, the scalar. We will have 2 divided by 9 times 9 divided by 14, the prior, divided by 14. This will give us 2 divided by 5. You can actually calculate this one. Similarly, we have B of no and rainy, posterior, is the likelihood, no, probability of no, fires, and B of rainy, same. That's the reason why I'm saying this one and this one is not important. They are not actually like, they are not dependent on which class. They're independent. And you will calculate this one. 3 divided by 5. You can go over those numbers. 5 divided by 14 and 5 divided by 14. This will give you 3 divided by 5. So now, based on those priority, the posteriors 2 and 5, we will decide. B of no rainy. Is it greater or not? We will check now. B of yes raining. This one is 3. Sorry, this one is 2 divided by 5. This one is 2 divided by 5. This is 3 divided by 5. It's greater than 1. It's no. So we'll be deciding that this class is no. So we will not actually playing, because it has a likelihood of raining more than it has a likelihood for playing. So now this is actually relying on both the likelihood and the prior. So the question is, if I don't have the prior, will I need to continue up to here? I will decide based on this, only the likelihood. If I don't have the prior, or if the prior is equal. Most likely, if the prior is equal, then our decision will be based on the likelihood of that feature based on given for omega 1 or omega 2. This is only for one feature. So do you have any question about this example? Yeah, could you please explain what you mean again by if it is or isn't a condition? So before we will actually calculating those probabilities based on the priors. There is no condition. It's always fixed all the time. But now we are adding more features, more information with a condition. This condition is called the likelihood. This condition is called the likelihood. That's the reason why it's condition here. What is the probability of raining given yes? What's the probability of raining given no? That's called the likelihood. So most likely, the most important thing that we'll be dealing with when we have normal distributions is how to call or to calculate those distributions. So now if we have more than one feature, if we have more feature, not only like the weather, which is rainy or sunny, we'll have x1, x2, xd, and then d is the number of features that we have. For fish, we will have like lightness and length, 2 dimensions. And for some classes, we might have more. So generally, we will have xd features, where d is the number or the dimension. And we have also omega c, we will have c classes. We want to actually build on those huge number of dimension for the features and also classifying them to C classes. So for example, weather and temperature. Yes, for example, weather and temperature. Or for example, like weather and wind. Is that right? That will be our next example here. So one of the things that it's difficult to calculate for the Pias rule or for the Pias like formula is if the events are not independent. If they are not independent, then it will be very difficult to calculate. However, most of the time we will be dealing with if the events are independent. So for example, here, this is the posterior class omega k, given that I have a set of features. It's actually a vector. So you might see here, this is x1, x2, all the way to xd, where d is the number of features. Is that right? In that case, how can we calculate? It's very difficult to do that, but usually what they do, we assume that there is an independent events between those features. So for example, here, we will have the likelihood of x1 given omega k, x2 given omega k. Is that right? If I don't have those features, then I will be actually calculating here is x1. Well, here is x1, x2, and omega k. That's called the chain rule of probabilities that we did before. But now we don't do that. We assume that it is independent. This event is independent of this event. x1 in omega k, x2 in omega k, all the way to xd in omega k times the prior divided by scalar, which is a constant. I will come back to this one if we have time, because this you can just read it yourself. Here I added a new feature. Instead of the weather that we used, I actually added a wind here. And now, based on my new data set, I want to calculate either to play or not based on the wind is being moderate and the weather is sunny. 2 features. And we will assume the independent. If we have time, I will come back to this and solve it. But if I don't have time, you just need to read it, which is straightforward. And you will have my complete solution. Okay, let's go to more stuff about this. So now back to the decision theory. When you decide about being salmon or sea bass, you will have to pay the cost. Is that right? For example, you went to the shop and you want to buy one of the fish. Is that right? Salmon. Most likely, if you want to have salmon and then they misclassified sea bass as salmon, you will say, okay, that's good. I like to have salmon. That's the cost that you will get, either a good cost or a bad cost. Here we are saying that we have a concern with a relationship between the choice of decision boundary and the associated cost. So what will be the decision theory, or the boundary is threshold, is that right? Threshold is the decision boundary. We represent it as X star. This X star will actually determine what is our edge between omega 1 and omega 2. What is the boundary between omega 1 and omega 2? So we want to choose this one carefully such that we minimize something called cost. It has to be chosen to minimize some notion of cost. For each decision that we are going to, you will have a different cost. Let's take an example of this. I have a likelihood that I give it to you, and I want you to choose the decision, the boundary. So in general, we want to reduce the chances of making bad decisions. Okay, Salomon versus Seabass, or Seabass versus Salomon. What do we mean by a bad decision? You have this model from your machine learning or from the histogram that you did, or an expert guy who did this one because that guy knows what is the feature of Seabass, what is the lightness of Salomon, and they build this for us. So now, if I choose this boundary to be here, forget about this. If I choose it to be here, what do you think? This is good or bad? Again, if I choose it to be here, the boundary has to be chosen such that we have the minimum cost. We don't want to go with this side, because if you go with this side, this will be only for Salomon, or a small region, but the huge one will be for Seabass. That will be bad. Is that right? Because if you choose X to be around 3 or 4, the value for being Salomon, as for the likelihood, is greater than the value for being Seabass, and then you will be misclassified. That's a bad decision. Is that right? Similarly here, if you go here, you will say, okay, all these things is for Salomon, and the remaining is for Seabass. Still, you are deciding here to be Salomon, but the feature has a lot of values, has a lot of counts for Seabass. That will give us a bad decisions. Is it right? So this region, the boundary, has to be chosen carefully. So how do we choose it? That's actually what we will be calculating. We don't choose it like randomly. We will be calculating over math. So here, I choose it here to be, or they choose it here to be X star. Do you think this is good? Do you think this is good? I think so. Why is that? There are a lot of students said yes, yes, yes. Thank you, guys. Minimal overlap, that's correct. Split eventually. Minimum error. This all good answers. Yes. So when you think about the boundary, what is the important thing that you will care about? Is actually the region around the boundary. That's actually the main point where the Seabass can be misclassified as Salomon. Here, this is what we care about. This one is too different than this one, and we know it. But the one that actually we have is this one. If you think about this point, this red, the error of misclassifying is less than this, then we'll say we are good. Is that right? Here, the black curve here, the black histogram for Salomon is less than this. We are good. So we will be like deciding to be Seabass, and that's actually the critical point. However, this error is also a problem. Is that right? If there is a noise in the data set, this error might be increased. This is the error, the tail, or the error for being Seabass in Salomon. This is the error for being Salomon in Seabass. We want to minimize this error. So the question is how to minimize this error. And when we learn about normal distribution, this error will be the tail of the normal distribution. Okay, the erroring value seems to cancel out. Okay, so how do we minimize this error? One of the main things that we minimize this error is we select the very good features. We try to make sure this is almost zero. This is almost zero, which is not possible, but we will try to minimize it as soon as possible. And then if you think a little bit back, I want to go to the length. Well, this one is still lightness. This is the length, is that right? I think you can see clearly. this feature is bad compared to the lightness. Why? Because we have a lot of error here, and we have a lot of black histograms here. This actually will create a problem when we do classification, when we do testing. But for the lightness, that actually we had, it's better than this model. So choosing your feature carefully is a key point to reduce this error. Adding more features, exactly. We can actually add more features and make it into higher dimension, because you might have differentiation in the CBAS and Solomons, but that will actually make the models complex. But in general, yes, we increase the number of features. Let's go and see how can we model the likelihood using normal distribution. Okay, this is actually the error. That's actually the error we want to minimize. We have 2 minutes. I will stop here and we'll be replying to your questions if you have. Otherwise, we will continue at 8:10 or 8:08. Okay, so I don't understand what we want to be independent. I think you are referring to where I said the features needs to be independent to be able to find the bias rule. Without being independent, then we might have a problem calculating the bias rule. But if the features are independent, then that bias rule is called naive bias rule. So if we go back to this one, probably you're actually mentioning about this. So here we want to calculate the posterior of class omega k, given that we have a set of features. So by definition, the posterior is equal to the likelihood times prior divided by the probability of the feature. That's by definition. So now we want to find the likelihood of omega k with all of those features. That's actually dependent. Is that right? If we don't have that assumption, so for example, let's go back and define what is the chain rule of probability. So if we have probabilities like this, omega k, we have x1 and x2, only 2 features. This one is a vector of 2 dimensions. How do we calculate this? So we will have omega k be, for example, like this, x1, then we will have b of omega k x given x2, and so on. This is like the chain rules of the probability. This is not independent because you are saying x1 given x2 or given x1 and x2. Those are probabilities that are dependent. What we are saying here, we want actually to make the probability of omega k given x1, then the probability of, omega k given x2. Those are independent. Those are independent. And in terms of likelihood, we will say x1 given omega k times x2 given omega k times xd given omega k. Those are independent. Means my feature of that sample related to omega k is different that of the other feature of that sample related to omega k. They are not independent. They are not dependent, sorry. I hope I answered your question about the independent. Let me write this one again here, so you will explain it when we come back. That's what we care about for now. Just write this one before we come back, and then we'll be moving forward. Okay, so can you provide a document or guidelines? Yeah, I might. Okay. Yeah, I might prepare like a document for this. Yeah, I will do that. It shouldn't be like a lot of guidelines, just a small steps that I will explain. And also I will explain how I will be grading your project. Okay, we will have 1 more minute, and we'll be starting this third lecture. Okay, guys, we'll continue. So here I just wrote a few things, a few sentences for clarification, where we have an error here for CBAS being misclassified as Solomon, as red one here, and then this black one here. So the question is, what is the error of that sample given X in our model? What do you think about the error? What is the error? Do you have any guess? Do you have any answer for this? What is the error of misclassification for a feature, for a sample with feature X? Okay, let's write this one. So the probability of error, This is how we calculate it. I'm waiting for answers, but okay, let's do it. So the probability of error given X is that we have two possibilities. Is that right? Is the probability of misclassification, omega 2, the posterior of omega 2 given X, this is the probability of omega 1 given X. This is if we decide omega 1. This is if we decide omega 2. That's we call it the probability. Is you're actually deciding for the other class, which is misclassification. Is that right? So the probability of error for any sample with a feature X is you are actually giving the posterior of omega 2, but you are deciding omega 1. You are actually calculating the posterior of omega 1, but you are deciding omega 2. It's the way around. That's actually, we call it the error. So for example, here, if we have omega 2, and this is a feature X, we might have the probability of omega 2 given X should be the measure because it has a lot of shadow here, point X or 0.9, and B of omega 1 of X is 0.1. So now, if we decide to go with omega 2, then the probability of error is 0.9. Is that right? That's actually if you decide to go with omega 2, but the decision was for omega 1. So it is the way around. This is only the probability of error for a feature value X. What is the average probability? How to minimize the error, and we find the average probability. So the average probability is called B error. It's not related to one value of X, but it's the average for the whole distribution. Since it's continuous from minus infinity to infinity, B error given X, the probability of X dx. So if you have a distribution like this, so you are actually calculating the continuous value for all X. And that actually is coming from the mean. That's actually coming from the mean. So you can imagine that this is the conditional BDF, and that's the probability. That's the average or the expectation of the mean. That's actually the error, which is the total error or the average error for the whole system. So now how to minimize this error? This one, probability of X, we don't have a control over. It's a scalar, as I mentioned before, but we will have actually a control over this. So now, to minimize the probability of error, we want to minimize that term. And minimizing this term is by making a correct decision. By making a correct decision. Is that right? It's like to minimize this one, which is basically this one because they are linearly related. Either you minimize that or this, same. So now, if you want to minimize this one, you will have to make a correct decision of omega 1 or omega 2. Means your posteriors have to be designed in a best way. That's actually what it means. If your posterior is not designed very well, then you will have a lot of error for this one. So you will design carefully B of omega 1 of X has to be greater than omega 2 of X. Those has to be a little bit differentiated to make a good decision for omega 1, and then omega 2 for the otherwise. That's actually the error. So you have two types of error, either the error, conditional error of X, which is the other way of posteriors, or the average error is over all the normal distribution. And we'll be calculating that when we have examples about normal distribution. This is actually just a repetition of the average probability of error, which is this. That's what we care about. We need this to be small. And this is the definition that I explained. And the minimum possible error is the minimum of the posteriors. You don't want actually to maximize the error through the posteriors. Is that right? The minimum possible of the error is the one you choose that you are getting. For example, if the posterior of omega 1 is 0.9 and the posteriors for omega 2 given x is 0.1, most of the time you will be choosing 0.9. Then the error that you will get is 10%, is 0.1. I hope this is clear. And also this is exactly if we have a decision rule with multiple features, and that's the total error. So the probability of EX, this is an error given x as a vector. This is the probability of x dx1, dx2, and dxd. So those are for all the features that you will have with multiple integrations. So now let's move to the most important things of this lecture. When we have multiple classes. So now assume that we have designed our posteriors to be like this. I have b omega 1 of x to be normal distribution, and I have b omega 2 of x to be another normal distribution. They have different means. This is one mean. This is another mean. They have same variance. When I say same variance, means the shape, either it's narrow or wide, is same as the black and red. And we have here a decision boundary. Is that right? This is only if we have. So now, if I ask you how many errors or how many classes will be in error, that will be easy to say. Is that right? Because we have only two classes. Either omega 1 will be misclassified as omega 2, or omega 2 will be misclassified as omega 1. So the question is, how do we find this for normal distribution? How do we find this point? This intersection between them. So now, if you think about this, if you continue this one here, that's the tail of the other normal distribution, and this is the error. The other way, this is the tail of the other distribution, and that's the error. It's actually good to minimize that region, the overlap region. We want to do that, is that right? But the question is, how do we find this point? By finding this point, then we'll be differentiating. This is for omega 1, this is for omega 2. This is for omega 1, this is for omega 2. I will go slowly over those because those are very important. It's a Gaussian distribution, okay? That's a Gaussian distribution. It's normal distribution. So here, for two classes, we will have one possible misclassification. Misclassification, is that right? That has to be around the boundary. This is for two classes. This is the boundary, and we might have a problem here or there around the boundary. And we will go forward finding this point. So now let's assume we have multiple classes. This is the posterior that we designed based on the likelihood and the prior. We have another posterior for omega 2, third posterior for omega 3. And we model this, assume that is given to us. We want actually to find the decisions, is that right? So the intersection between those normal distribution, when both of them are equal, that's the critical point. Then it goes up or down, we will differentiate. This is the critical point where we cannot make a decision. The posteriors are equal at this point. Then there will be an error. So here we have one error. Here we have one error. But if x is here, then I have a value here, another value is there, another value is there. Is that right? Then my classification will decide about the maximum point we have, which most likely is this. Is that right? It will say b omega 2x equal to 9 is greater than both of them for omega 1 and omega 2, for omega 3. Or you will say it's the maximum with I of b of omega I x. That will take the maximum value for class I, which is 2. Anyhow, those are two different things we will actually go over. So the minimum error rate classification for multiple classes is same as the bias, but it has a different actually name. Sometimes we call it the bias rule, sometimes we call it the minimum error rate classification, the total summation of all the posteriors has to be 1. That's the sample space. And the error of AI equal to X is the one that you are choosing for a different class, where I is not equal to J, or it's 1 minus the accurate probability. It's 1 minus the accurate probability. And we will go over this one. So we can generalize this. So this is one of the most transition from bias rule to discriminant function. That will be the topic for next lecture. So generally speaking, some of the times we don't want to go with probabilities. Is that right? Sometimes we really don't want to go with the probabilities, but what we will be doing is we will do some mapping. Instead of calculating B, then B, and B all the time, we will do some mapping to functions. So instead of dealing with probabilities, we might actually define it as a function. This function might be easier for us to manipulate. It might be easier for us to shift. It might be easier for us to scale. And that's actually what is going on here. So now the generalized pattern classifier is we decide omega I if it is greater than omega j for all of I not equal to j, but instead of having b of omega I of x, we will now, from now on, we will represent it as gi of x, where gi of x is a discriminant function. It's a function that will differentiate between omega 1 and omega 2. Okay? That's one point. So now we are actually transforming from probability side of notations to functions, which is j omega I. Let me see my notes, what's going on here. Okay, so now instead of saying that b omega I given x, the posterior of omega I is greater than omega jx, we will say gi of x is greater than gj of x, where gi and jj are the functions that we'll be building on. So now, if you have the posterior that rely on both prior and likelihood, this is called MAP, the maximum posterior rule. And I think this is very famous for you guys. If our decision is relying on prior and the likelihood, both on the numerator that we defined before, we will actually call it the MAP. It's maximum posterior rule. However, if the prior probability of a class omega 1 and a class omega 2 is equal, we ignore them, then we will be relying only on the likelihood. And that's called the maximum likelihood rule, ML. So usually we go either with MAB if we have priors, or we care about the likelihood if we ignore the priors. So if you go back, I want to go back to that definition. Let's stop here. So this is our posteriors. If it relies on likelihood and priors, we call it MAP, MAB, maximum posterior likelihood. If it relies only on the likelihood, it's not care about it. They are equal, 0.5, 0.5, or 0.33, 0.33, and 0.33. We don't care. Then this is called ML, maximum likelihood. That will be modeling using normal distribution. Okay, so what is the implications of mapping gi of x as b omega I of x? What is the implication? So sometimes, in general, as I mentioned, it is useful to replace bi omega I x as gi of x. Can anyone tell me what function it comes to your mind to do this? So ML has no prior probability. Exactly. ML has no prior probability. It relies only on the likelihood. So anyone has a function in his or her mind that will do the mapping. It's an easy function to deal with. So now we want to map normal distribution. Yeah, that's normal distribution will be actually like we will model the likelihood using normal distribution, but I want to have a general function represented by gi of x to represent this probability. Okay. Think about a function that monotone increasing, like this. What is this function? This function is x, gi of x. It's actually increasing with increasing x. Does anyone has the name of this function? Yes, exactly. There are very good on transfer function. This function is the natural log. It's ln x. It's the natural log. So now, instead of doing this one as probability, we will actually be dealing with the function is called the natural log. Why do you need to do with natural log? Let me give you like some keys here. So you know that for normal distribution, mu and sigma is 1 over 2 pi sigma, is that right? Sigma square exponential of minus probably x minus mu square divided by 2. This is actually the normal. It's monotone increasing. Yeah, that's a good answer. The natural log is monotone increasing. Let's take a very simple normal distribution. It has a mean, variance, and it's defined to be this. You don't have to memorize this. You just need to understand it. So now, if I have another one and I want to find x, dealing with exponentials is difficult. For mathematical relations, for notations is difficult. What we need to do is we need to map this one, the posteriors, giving that it's normal, to a natural log. Why? Because the log will be canceled with exponential. And then we'll be dealing exactly with x. And we will come to that point. So now we want to replace this posterior by a mapping function that is monotone increasing, which is natural log. It's monotone increasing. That's actually called the natural log, ln of function. Okay. Why is that? Because this, first of all, is monotone increasing. Second, it has a derivative. Third, it's good to make scale, shift, and transition of those functions. Whatever you do for this, it will not affect your decision. It will just affect the function itself, but the boundary will be the same, as we will see a few examples. So now, given this implication that I just explained, we want to define f of x is equal natural log. Then we will have gi of x is the posterior b omega I given x, which is the likelihood, the prior divided by bx. We don't really care about bx, but that's fine. Now gi of x, let's represent it as bx omega I b omega I. I don't care about this. The natural log of gi of x is equal the natural log of all of them, bx of omega I b of omega I. Is that right? Is there any simplification that we can do for this? We know that when we have a natural log and these two functions are multiplication, they becomes what? Addition. Exactly. Thank you. It becomes addition. So we will have ln or natural log of bx likelihood plus. So now, given that those are addition, I can definitely manipulate this alone, and I can actually manipulate this alone. That's actually one of the best simplification. Is that right? Sometimes if I don't have the prior, I will cancel it. I will deal only with this. And now this natural log will be canceled with the exponential of normal. Will make things easier for us. Anyhow, we will continue with this. And this will give the same results. So let's go with two classes. So we have plus or minus. Then we will be defining two discriminant function, g1 of x, g2 of x. we will assign this to omega 1, we'll assign this to omega 2 if g1 of x is greater than g2 of x, if g2 of x is greater than g1 of x. So instead of doing now posteriors, we will be mapping them into natural log and compare the values of g1 of x, of g2 of x. In terms of two classes, we usually don't need to go with comparison. This is 5, this is 2. Is that right? This is 6, this is 2. We don't want to go with that. Sometimes we will be defining one discriminant function, which is the difference. Sorry, this is 1 minus g2 of x. Now our decision is based on the sign. Either it's positive or negative. If g1 of x is 5, g2 of x is 2, then our decision will be greater than 0 or less than 0. Now, instead of having values, we will actually be deciding based on the sign of g of x. Greater than 0, we will have omega 1. Less than 0, we will have omega 2. So all of those are just manipulations that we will be dealing with normal distribution. This is only applicable if we have two classes. This is if we have two classes. It's binary classification. So now, two things that you can come up from this slide. I don't want to explain this one again. This is the way that we represent it as a posterior. That's what we did before. This is the way that we represent it as a natural log. I just plug in those len here. I make it like multiplication. Then we have like minus len log 2, which if we take the difference between them, then I will end up with the minus is a division in natural log, and the multiplication is addition. This is the way that you need to learn. So we have len x dot y is natural log of x dot natural log of y. We have len x divided by y is len of x minus len of a. You need to know those things in order to proceed with the more advanced math. This is called the log likelihood. So now if we want to link this one to machine learning, you will define those features as inputs. We have number of D features. This is called the structural like function. D of features, we have C number of classes. Each class will have a discriminant function, posterior, that we defined before. And now based on those linear relation between x1, x2, x3 with g1x, g2x, gcx, you will actually decide which class is the most one that will have for your decision. So if g1 of x is greater than all of them except g1 of x, then you will decide g1 of x. That's actually the classification of the action here. That's actually how you will do this one. We will design this as a neural network. It has an inputs, hidden layers, and that's the output. And we will have like a common function, which be represented as an activation function. We will learn this one later on. So now the bias rule that we learn is how to model the likelihood. First of all, we agreed that to calculate the prior, either we have small data set that I did in the example, or we can just estimate it. We can estimate them from the training set. It's a proportion of samples from each class could be a starting point. This is for the prior. For estimating the likelihood, we will define it as a Gaussian model. Some of them, they design it as a histogram, but since we are actually dealing with normal distribution, either univariate or multivariate, we will be dealing with Gaussian distribution. So moving forward, we have 30 minutes, talk about two examples. So now, how do we design the likelihood? This is the point we will be looking at from the beginning. How to model the likelihood, which is the probability of x given omega I. That's the likelihood. That's the first term of the numerator of the posterior. How do we design this? So if you have a feature with one dimension, we will be dealing with the univariate Gaussian. This is one dimension. Means this is one dimension. It's not D. D is equal to 1. And that's actually what we wrote it before. It's 1 over 2 pi sigma I, an exponential of the difference between the feature and the mean square divided by sigma I. Okay? And here is the bell shape of Gaussian. The Gaussian has a bell shape like this. It has a mean. It has the peak here, where the mean where x equal to the mean, and here is the standard deviation, which how the data is scattered around the mean. Let's take this example, and we'll go like step by step here. So my first example is that I have two classes. One is omega 1, one is omega 2, and the priors of those classes are equal. B omega 1 is equal to B omega 2 is equal to 0.5, and the mean of them is 0 and 3. So now we want to model the likelihood. Is that right? This is the first distribution. It has a mean of 0. It has a variance of 1. It has a mean of 3. It has the variance of 1. So both of them have the same variance but different means. Let me plot this one here. We have x as my feature. It's one dimension. That's what we start with. It's univariate. And the mean is 0. That's my 0. So we will have 1 is here. This is the L shape of the first Gaussian. And that's the peak. We will call this one is Bx of omega 1. This is for class 1. Okay. We will define another one that has a mean of 3 and it has a bell shape. Okay, those are two. This is B of x given omega 2. This is the peak value. This is another peak value. This is for omega 1. This is for omega 2. And here we go. That's the error. The first question is find the decision boundary. Find the decision boundary. Anyone can answer this? That's the first question. The second question is, will this be ML or MAP? Maximum likelihood or maximum posterior? Which one? Which model we will go with? Okay, I have answers here. It's ML, max posterior. Let me review what the difference between them. When we say the posterior means it relies on two things, the prior and the likelihood. Is that right? But when we say it's maximum likelihood, we really ignore the priors. And here, since we actually have the priors are equal, I don't really care what is the knowledge, the prior knowledge of which class, because both of them is 0.5. And then our decision will be relying on the normal distribution of this or this. That will be ML. So in this case, I would say ML is equal MAP because that is ignored. Equal probability. So now we will say choose omega 1 if B omega 1 of x is greater than B omega 2 of x, which I can actually write it as x of omega 1 likelihood is greater than x of omega 2, because there is no prior knowledge here, there is no probability here. So the boundary, how to find the boundary? How to find the boundary? I'm still going back to my question, how to find the boundary? Think about this joint, this point. This point actually happens when the likelihood are equal. This intersection is happened when this tail and this tail are intersecting. They're equal. Is that right? So finding the boundary means that B of omega 1 x is equal B of omega 2x. That's actually the case. Is that right? So you might have this one with the priors. Let me write it again. Bx of omega 1, b omega 1 divided by bx. This is the posteriors. Then we will present it as g x of omega 2, b of omega 2 divided by bx. This will be cancelled. Sorry, this one and this one will be cancelled. Prior probability will be cancelled, and we'll be relying on the likelihood. That's the reason why we say likelihood. Okay? So now, moving forward, for first class, N 0, 1. What is the distribution? Anyone? So, but what if the distribution are, yeah, if the distribution are not identical, we will have that case. Wouldn't that bias your model? Yes, exactly. That will bias our model. But let's go with the identical and the ideal solution, where they have the same distribution, have the same variance. And then we will go also with different variances and also with different prior knowledge. For N0, 1, then probability of X, the distribution of this one X given Y, given omega 1 is 1 over square root of 2 pi. Sigma square is 1. I don't care about it. It's exponential of minus X minus mu square. Mu square is 0. I will not care about that. I will just write it right away. Minus X square divided by 2. And this variance is 1. For N0, 3, the probability of X given omega 2 is 1 over 2 pi. Then we'll have exponential X minus 3 square. This one is, this is wrong. It should be 3, 1. X minus 3 and the variance is 1. Let's go back here. It's 3, 1, yes. It has the same variance but different means. We have now those two equations. We just need to make them equal to find the intersection point. B of X omega 1 is equal, B of X is omega 2, where we have 1 over 2 pi exponential of minus X squared divided by 2 is equal 1 over 2 pi exponential of X minus 3 square. Is that right? It's actually divided by 2 here. We will have minus 1 over 2 here, minus 1 over 2 here, just to make it same as the multivariate. Okay, so now when we have this one is equal, those will be cancelled, and we will have only those exponentials. So now dealing with exponentials without the natural log, why didn't you divide with second? Yeah, we actually did. Thank you for this, for correcting me. So we divided by minus 1 over half, minus 1 over half. If we go back, it's here, minus 1 over 2. Okay? But we really ignore this. We really ignore this because they are being 1 in both cases. I think my writing is clear here. So now, dealing with exponential here and exponential there is difficult to find X. That's actually the reason why we need to find what is the point of X here. It's just to make them equal. That's the intersection. So now by taking the natural log to both sides, what we will get? It's ln exponential minus X squared divided by 2 is equal the natural log of X minus 3 square. 3 square. Okay. So when we have natural log and we have exponential, they will be canceled each other, and we will get only this one. This will be canceled, and we will have only that one. Is that right? So we will having minus x squared divided by 2 is equal minus 1 over 2 x minus 3 squared. This will be cancelled. Minus will be cancelled. We will have only x squared equal x minus 3 squared. So now we can find x. This is like quadratic function. We can definitely find x. X squared equal x squared minus 6x plus 9. This means 6x equal to 9. This means x equal 3 divided by 2. So here is 3 divided by 2. 1.5. It's between 3 and 0 because the variants are identical. 3 divided by 2. Okay, so now we found the boundary. Is that right? I hope if everyone is following because those examples are important. The type of midterms and final is something similar to this. I will not be explaining how to multiply matrices or vectors. It's something that you need to design your normal distribution, finding the boundary and decide. So now we found that this x is equal to 3 divided by 2, and it will be easy from the beginning. That is halfway point between the two normal distribution. Why is that? Because they have actually the same variances. But if the variants are different for each normal, then you will not do that. You will get different point. Actually, you will get 2. Why not just get average the means? Yeah, that's actually one point, but we want actually to go step by step. Why not just average the means? That's actually one point to take the step. But when you do this one for more complicated stuff, where the variances are not equal, or even the covariance for multivariate are equal, you will follow the same process. Is that right? So this is one thing we find. Making a notes here, since both Gaussians have the same variance, the same sigma square, this is a very ideal solution, ideal case where it's halfway between μ1 and μ2. So which question are like midterms can you repeat? So the questions about the midterm is something like this. It's something from my examples and problem sets. So why is exponential minus 1 over 2 only on one side? I think it's in both sides. So this is minus 1 over 2 in one side. This is minus 1 over 2 in the other side. I have it here and I have it here. I think it's there everywhere. Otherwise, my solution will be wrong. It's here and it's here. Yeah, it's both sides, but I actually forgot it at the beginning. Then I just learn it later. So now let's do another case before we finish this lecture. If the means like different, that's fine. The means are different, it doesn't make any much difference. But if we have a different variance. So what do you think, guys? For now, I will make it simple. I will make this one is equal. Each one is 0.5. So now we will not care about the MAB. We will be caring about we will not be caring about the MAB, we'll care about the ML. So now, what do you think about this one? So omega 1, it has the same example as example 1, and omega 2, the mean same, but the variance is 4 times. Okay, I will give you the hint how it will looks like, then you will be solving it. I will plot this one. This is my x. The first normal distribution, what is 0.5? 0.5 is, you mean like 1/2, which is the 0.5 that comes from the normal distribution? If you are asking about that, that's the definition of normal distribution. If you are saying something else, then you please be specific. So here we have the normal distribution of both. One of them is here. It has a mean of 0. Sorry, my drawing is not good. And the other one has a mean of 3. But what do you think about the shape, the L shape of this one? Is it same as this? It's narrower, wider? What do you think? Wider, yes, but flatter, yes. Wider, thank you so much. Those are good answers. So, and how about the peak value? Okay, now I'm asking a lot of things. So how about the peak value? This is the peak of the first normal distribution will be shorter, is that right? Think about it. Let's go back here to our like original. We calculate the peak when x is equal to the mu. Is that right? That's the peak. If x is equal to mu, this exponential to 0 is 1. Then we will have only 1/2 pi sigma I. Go back here. For the first one, we will have 1/2 of 2 pi sigma square. If sigma square is 1, we will have 1/2 pi. This is 1/2 pi. Now, in the second case, we have 1/2 pi sigma square, which is 4. 1/8 pi. Shorter. Thank you for those who said shorter. Is that right? Peak will be shorter. And then it will be, sorry, why I'm doing this? You might have something like this. Smaller, wider. And if you think about this, actually this should be like a better one. Let me erase this. This should be narrower because I want to arrive at a point where we have two intersections. This is narrower and this is wider. So when we continue this one, the red one, and this is narrower, it actually we have one intersection here, one intersection there. This is actually the main difference where we have an ideal variance, both of them, we will have only one intersection, but when this is wider, it's still wider here, even though we are going left. This is narrower, going to 0 faster than the one it has large variance. I hope this is clear. 1/8 pi. So this is for omega 1, this is for omega 2. So now when you have, that's actually the horizontal bounds is minus infinity to infinity. Yes, the normal distribution, the tail of the normal distribution is not going to 0, but it's going decaying all the way to minus infinity and infinity. So it's going all the way here, minus infinity to plus infinity, but it arrives at that point when it is 0. Okay, so now instead of having this one and this one, we will have 2 points. This is my first region, this is my second region. So now which one is omega 1, which one is omega 2? Which one, where are my decisions? I will be waiting for answers if you have, otherwise I will just answer it myself. Again, this black one is for omega 1. This red curve, normal, is for omega 2. So now, which one here is omega 1, which one here is omega 2? How about this? So what do you think, guys? Think about it. So we will have here, this is for omega 1 definitely. This is for omega 2 definitely because it has high values here. Since this red is greater than the black, we still have omega 2 here. And that's actually the main reason why the variance of the second normal distribution is bigger than the variance of the first normal distribution that goes to 0 quickly or goes to small value quickly. So the answer to this one is how to find this point. And this point is you need to follow the same process that I did here. You just need to follow the same process. Nothing actually else. Make it equal gi of x, g1 of x is equal to g2 of x based on the posteriors. Then you will take the natural log and you will do some simplifications that you will be dealing here, as I mentioned here. Then you will be solving this quadratic formula where you will get x1 and you will be getting x2. So two values will be here. And that's the final answer that you might get. This is my x2 and this is my x1. So which one is important? x1 or x2? Which one is extreme? Which one is related to the outlier? Sorry. So x2 is the important one, or x2 is the extreme? It's actually the extreme, exactly, because at this point you might not have C features with those values. Is that right? Most of my features based on the learning is around the mean, but those will be related to the outliers, which we might not care about. So this feature is the best decision that I might have. This is also considered as another decision, but it's not important than this. So here is the final slide for this lecture based on the Bayes rule that we explained, based on the discriminant function. Next time, we will be moving from univariate with one class with one feature to multivariate with multiple features, where we will not be dealing with the variance anymore, but we'll be dealing with the covariance, that matrix we learned. So I will stop here. Let me know if you have any question. We still have 5 minutes.